Hello, in this lecture we'll answer two questions. In the first question, we'll find out the area of this green shape. In the second question, we'll find out the length of line segment AP is equals to x using two different methods. So we start with the first question. In the drawing, we have this semicircle. We know that BC equals to 10 units in its length. That is to say, the diameter of this semicircle is equal to 10. And we also know that PC equals to 8 units in its length. This is angle ABC, that is the right angle. Again, our task is to find out the area of this green shape. So, first of all, we'll join points P and B together by a straight line. By joining points P and B, we created peripheral angle BPC. Peripheral angle BPC subtends on BC, that is the diameter of the semicircle, and we know that according to rule 5, any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in its size. So this is peripheral angle BPC is equal to 90 degrees in its size according to rule 5. So click quickly on rule 5. According to rule 5, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. So in the drawing, you have a circle. AB is the diameter of this circle. This is peripheral angle AEB that subtends on AB, that is the diameter of the circle. And therefore, peripheral angle AEB equals to 90 degrees in size according to this rule, rule 5. We have already implemented rule 5 in our drawing, because in our drawing we have peripheral angle BPC that subtends on BC, that is the diameter of the semicircle, and therefore peripheral angle BPC must be equal to 90 degrees in its size. In the next step, we implement the Pythagoras theorem on this right angle, triangle BPC. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here by PT is the relation for Pythagoras theorem. The hypotenuse on the right angle BPC is BC, and therefore the square of the hypotenuse is BC square, and BC square must be equal to PB square plus PC square. Which again, according to the Pythagoras theorem, in this right angle BPC, BC square equals to PB square plus PC square. The hypotenuse BC equals to 10 units in its length, therefore BC square is 10 squared, that is 100. And it is equal to PB square. PB is the missing side, so leave it as it is, plus PC square. PC is 8, therefore PC square is 8 squared, that is 64. So in total, we found out that 100 equals to PB square plus 64. Here we subtract 64 from this equation, and we get that 100 minus 64 is 36. So 36 equals to PB square. Here we take a root out of this equation, and finally we get that PB equals to the square root of 36, that is 6. So the missing side PB is equal to 6 units in its length. PB equals to 6 units in its length. In the next step, we define the center of this semicircle. This point is point O. The radius, the diameter of this semicircle is 10, therefore the radius must be equal to 10 over 2, that is 5. So the radius OB is 5, and the radius OC is also 5. In the next step, We join points O and P together by a straight line. OP is of course the radius of the semicircle, that is 5. So in the next step, it is given us the question that AC is a straight line. AC is a straight line, so if you focus on the left side of the straight line AC, it's point P. Here the sum of the angles must be equal to 180 degrees according to the rule 3 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of AC at point P? We have this angle that is the right angle, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we define angle PAB, this angle as alpha. So in the right triangle APB, this angle equals to alpha, this angle equals to 90 degrees. Therefore this missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. We know that the big angle ABC is the right angle. This is angle ABP, that is equal to 90 degrees minus alpha in its size. Therefore, this missing angle, angle PBC, must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees. That is the size of the big angle, angle ABC. So in the right angle BPC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we will prove that the right triangle APB is similar to the right triangle BPC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we should find out that all the angles of the right triangle BPC are correspondingly equal to all the angles of this right triangle APB. And therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down, and we should find out that the right triangle BPC is similar. This is the sign of similar to the right triangle APB, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB of the right triangle APB over side BC of the right triangle PBC is equal to side AP of the right triangle APB over side PB of the right triangle PBC. And we also derive that side PB, actually side PB is a common side that belongs to both triangles. So side PB of the right triangle APB, so it is equal to side PB of the right triangle APB over side PC of this right triangle PBC. So repeat again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side AB of the right triangle ABP over side BC of the right triangle BPC is equal to side AP of the right triangle APB over side PB of the right triangle APB, and it is also equals to side PB of the right triangle ABP over side PC of the right triangle PBC. AB is the missing side, so we leave it as it is. Over BC. BC is 10 according to what is given as the question. And it is equal to AP. AP is the missing side, so we leave it as it is. Over PB. We have already found out that PB equals to 6 units in its length. And it is equal to PB, that is 6, over PC. PC is 8. So in total, we actually found out that AB over 10 equals to AP over 6 equals to 6/8. So those two expressions that are equal to each other, so we get equation 1 from those two expressions that are equal to each other. So according to equation 1, we get that AP over 6 equals to 6/8. AP over 6 equals to 6/8. Here we multiply this equation by 6 and finally we get that AP equals to 6 times 6 is 36 over 8. So here we divide both the numerator and the denominator of this number by 4, and we get that 36 over 4 is 9, over 8 over 4 is 2. So in total, we actually found out that AP is equal to 9/2. AP equals to 9/2. So this is side AP, is equals to 9/2. In this long equation, those two expressions are equal to each other, therefore we get equation 2 from those two expressions. According to equation 2, we get that AB over 10 equals to AP over 6. AB over 10 equals to those two expressions are equal to each other, therefore we get equation 2 from those two expressions that are equal to each other. So according to equation 2, we get that AB over 8 equals to 6/8. And again, according to equation 2, we actually found out that AB over 10 equals to 6/8. Here we multiply the equation by 10 and finally we get that according to equation 2, AB equals to 10 times 6 is 60 over 8. So AB equals to 60 over 8. Here we divide both the numerator and the denominator of this number by 4, and we get that 16 over 4 is 15, over 8 over 4 is 2. So in total we should find out that AB is equal to 15 halves. So I write it down in the drawing that AB equals to 15 halves. This is side AB, that equals to 15 halves in its length. In the next step, we'll implement, actually we define this angle as theta, and we'll implement the law of cosines in this triangle BOP. So what is the law of cosines? Actually, the law of cosines is true in any triangle. In any triangle, the following equation is true. Actually, this is angle theta. AB equals to B unit, AC equals to B units in its length, AB equals to A units in its length, BC equals to C units in its length. According to the law of cosines, the following equation is true. That cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. And again, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. So, according to the law of cosines, in this triangle PBO, cosine theta equals to 5 squared plus 5 squared minus 6 squared over 2 times 5 times 5. So repeat again, in this triangle BOP, according to the law of cosine, cosine theta equals to 5 squared plus 5 squared minus 6 squared over 2 times 5 times 5. So cosine theta equals to 5 squared is 25, plus 5 squared it is 25, in total it is 50, minus 6 squared. 6 squared is 36. 50 minus 36 is 14 over 2 times 5 times 5. 5 times 5 is 25, and 25 times 2 is 50. So in total, we actually found out that cosine theta equals to 14 over 50. Cosine theta equals to 14 over 50. Our task is to find out the value of theta itself. So how we can find out the value of theta? In order to find out the value of theta, we will perform on the result of the operation on of this function cosine on theta. The result is 14 over 50. So we'll operate the inverse function of cosine, that is arc cosine, on the result that is 14 over 50. In this way we get the value of theta itself. So the opposite function of cosine is arc cosine. We'll operate the opposite function arc cosine on the result that is 14 over 50. And when we operate the opposite function of cosine on the result 14 over 50, this will give us the value of theta itself. For example, I will take the example of square and the root that are two inverse functions. if we operate the function of a root on the number 9, the result is 3. So now, if we want to get the original number 9, we have to operate on the result 3, the inverse function of a root. The inverse function of a root is square. So we'll operate the opposite function of the inverse function of the root, that is square of 3. So operate the inverse function of the root on 3, so it is 3 square, and the result will be 9. So you can see that when we operate the inverse function on the opposite, on the function, on the result of the function, you will get the origin number itself. So now, in order to get the value of theta itself, we operated the opposite function of cosine on the result 14/50, and this will give us the value of theta itself. Exactly like this example. So what is arc cosine of 14/50? Arc cosine of 14/50 is 73.74 degrees. So if you found out that theta equals to 73.74 degrees in its size. So this is angle theta is equals to 73.74 degrees. Our task was to find out the area of this green shape. In order to find out the area of this green shape, first of all, we have to find out the size of segment BP. This is segment BP. So what is the area of segment BP? From the drawing, it is very easy to see that the area of segment BP is equal to the area of sector OBP minus the area of this triangle OBP. Triangle OBP is an associated triangle because OB equals to OP equals to 5. PB equals to 6. So in total, we actually found out that the area of segment BP the area of this segment BP is equal to the area of sector OBP. This is sector OBP minus the area of this associated triangle OBP. So what is a sector? A sector is a portion of a circle enclosed by two radii and the arc between them. The green shape AOB is a sector. So it is part of a circle, portion of a circle, with two radii and the arc AB between the two radii. This is angle theta, that is the angle between the two radii, or the angle between the legs of the sector. And what is the area of this sector AOB? The area of sector AOB equals to the area of the circle, that is pi r squared, times the angle between the legs of the sector, that is theta, over 360 degrees. Repeat again, the area of the sector is equal to pi r squared, that is the area of the circle, times the angle between the legs of the sector, that is theta, over 360 degrees. So we use this new formula in order to find out the area of this sector, sector OBP. Actually, we know that OB and OP are the two radii of the circle that is that contains this sector, and the radius of the semicircle is 5. We already found out that actually this is angle theta. Angle theta equals to 73.74 degrees in its size. That is the angle between the legs of this sector OP. So the area of this sector BOP must be equal to pi r squared, that is the circle that contains the sector, times the angle between the legs of the sector, that is 73.74 degrees over 360 degrees. R equals to 5, because it is the radius of the semicircle, that is 5. Therefore r squared is 5 squared, that is 25. So pi r squared is 25 pi times, so it is 25 pi times 73.74 degrees over 360 degrees. So the value of this expression in total, it is equals to 16.088 square units. So if we found out that the area of this sector BOP is equal to 16.088 square units in its size, minus the area of this associated triangle PBO. In order to find out the area of this associated triangle BPO, we will go perpendicular to the base BP. BP is the base of this associated triangle BPO. So actually this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and BP. This point is point M. And we have the rule that says that the perpendicular to the base of an associated triangle bisect the base. The base BP is 6, therefore half of it is 3. So MP is 3 and MB is also 3. So in the right triangle MPO, according to the Pythagoras theorem, PO is the hypotenuse. 5 square minus 3 square equals to MO square. 5 square is 25, minus 3 square is 9, so 25 minus 9 is 16, so 16 equals to MO square. Here we take out of the equation and finally get that MO equals to the square root of 16, that is 4. So we found out that this, the height MO is 4. You know that the area of any triangle equals to the base of the triangle times the height over 2. We'll choose the base as BP times the height MO. MO is the height because it's raised 90 degrees with the base BP over 2. So the area of triangle in PO equals to BP times MO over 2. BP is 6 times MO is 4 over 2. 4 over 2 is 2, and 2 times 6 is 12. So in total, we should find out that the area of this associated triangle BPO is 12 square units. And the area of segment BP is equals to the area of sector BPO minus the area of the associated triangle BPO. That is to say, it is equals to 16.088, that is the area of the sector, minus the area of this associated triangle, that is 12. 16.00 minus 12 is equal to 4.088 square units. So if you found out that the area of segment BP is equal to 4.00 square units. Our task in this question is to find out the area of this green shape. So what is the area of the green shape? From the drawing it is very easy to see that the area of the green shape must be equal to the area of this right triangle APB minus the area of this segment VP. So if you found out that the area that we are looking for in this question, that is the area of the green shape, must be equal to the area of the right triangle APB minus the area of segment VP. What is the area of right triangle ABP? So I'll copy the right triangle ABP here and we'll find out the area of this right triangle. Side PB equals to 6 units in its length, and side AP equals to 4.5. 9 over 2 is 4.5. So the area on this triangle APB will be equal to the base AP times the height PB over 2. The base AP times the height BP over 2. The base AP is 4.5 times BP, that is 6, divided over 2. 4.5 times 6 is 27 over 2. 27 over 2 is 13.5. So the area of this right triangle APB is equal to 14.5 square units. Minus the area of segment BP. We have already found out that the area of segment BP is equal to 4.088 square units. So the area of triangle APB minus the area of segment BP is equal to 13.5 minus 4.088. It is actually 9.412 square units. And this is the answer to the question. So the area of the green shape, in total it is equal to 9.412 square units. Okay, again we shall find out that the area of this green shape is equal to 9.412 square units. So we finish with the first question. In the next step I'll present to you the second question and we'll solve the second question in two different methods. In the second question, our task is to find out the length of line 70 AP is equals to x. We have to find out the value of x. So in the drawing, we have a semicircle. AB equals to 10. That is to say the diameter of this semicircle is 10. BC equals to 6 units in its length. AP equals to PC equals to x. And our task is to find out the length of line 70 AP is equals to x. We have to find out the value of x. So first of all, we define the center of this semicircle. This point is point O. The diameter AB is 10, therefore the radius must be equal to 5. The radius OA is 5. The radius OB is also 5. We join points O and P together by a straight line. O is the center of the circle, P is the point of the semicircle itself, therefore OP is the radius of the semicircle, that is 5. So, by doing these constructions, we can deduce the isosceles triangle AOP. Triangle AOP is the isosceles triangle because AO equals to OP. So, in the isosceles triangle AOP, those two sides, they are equal to each other. And we have the rule that in front of equal sides in the triangle, there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other and their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha because they must be equal to each other. Likewise, the big triangle APC is also an isosceles triangle because side AP equals to side PC. So in this isosceles triangle, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. But this is angle alpha, therefore this angle must be also equal to alpha because those two angles must be equal to each other because of the fact that they are located in front of those two equal sides. So this angle must be equal to alpha degrees in its size. So in the big isosceles triangle APC, the sum of the angles must be equal to 180 degrees. That is to say, alpha plus this missing angle, in total they must be equal to 180 degrees. Therefore, this third missing angle, so this is the third missing angle, it must be equal to 180 degrees equals to alpha. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. So the missing third angle must be equal to 180 degrees equals to alpha. Likewise, in this small isosceles triangle APO, the sum of the angles must be equal to 180 degrees. So alpha plus this missing angle in total must be equal to 180 degrees. Therefore, this third missing angle must be equal to 180 degrees equals to alpha, according to the same rule. So in the next step, we'll prove that the small isosceles triangle AOP is similar to the big isosceles triangle APC. So we copy those two isosceles triangles in a new equation. We will prove that they are similar to each other according to angle similarity rule. What is the length of side AP of the isosceles triangle APC? AP in total equals to 10 plus 6, that is 16. So side AC of the isosceles triangle APC is equal to 16 units in its length. side AP equals to side PC equals to X. That is the line segment that we are looking for in this question. So actually, those are the two associated triangles that are coming from the original drawing. So why those two associated triangles are similar to each other? First of all, those two angles are both equal to 180 degrees minus 2 alpha, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are also equal, they are both equal to alpha, therefore they are equal to each other. So if we found out that all the angles in the big associated triangle APC are correspondingly equal to all the angles in the small associated triangle APO. So write it down. So the big associated triangle APC is similar, this is the sign of similar, to the small associated triangle APO. According to angle similarity rule. And from the fact that those two associated triangles, from the fact that those two associated triangles are similar to each other, we derive that the following relationship exists between their sides. We derive the side AC of the big associated triangle APC over side AP of the small associated triangle APO is equal to side PC of the big associated triangle APC over side PO of the small associated triangle APO. Repeat again, from the fact that those two associated triangles are similar to each other, we derive that the following relationship exists between their sides. We derive the side AC of the big associated triangle APC over side AP of the small associated triangle APO is equal to side PC of the big associated triangle APC over side PO of the small isosceles triangle, triangle APO. We have already found out that AC equals to 16 units in its length over AP. AP equals to X, that is the line segment that we are looking for in this question, and is equals to PC. PC is also X over PO. PO is 5. So in total, we have found out that 16 over X equals to X over 5. Here we cross multiply this equation, and you get that X squared equals to 16 times 5. So here we take a root out of this equation, and finally you get that X equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only with 5. So it is actually 4 times square root of 5. In terms of numbers, it is equals to 8.94 units in its length. So the answer to the question is that the length of this line segment AP is equals to X. It is equals to either 4 times square root of 5 units in its length, or in terms of numbers, the length of AP is equals to X is equal to 8.94 units. So we finish with the first method. In the next step, I will present to you how to find out the length of AP is equals to X according to the second method. In the second method, we'll use the rule that states that the perpendicular to the base in an isosceles triangle bisect the base. Again, we use the rule that states that the perpendicular to the base in an isosceles triangle bisect the base. Triangle APC is an isosceles triangle because AP equals to PC equals to X. So from point P, we draw perpendicular on the base AC. Actually, we know that the base AC equals to 10 plus 6, that is 16. So write it down. The length of the base AC is 16 units. So from point B, we draw perpendicular on AC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and AC. This point is point M. And according to the rule that I mentioned, the perpendicular PM to the base AC or the isosceles triangle APC bisect the base AC. The length of the base AC is 16. The perpendicular PM bisect the base. That is to say, the first half, that is AM, will be equal to 8. The second half must be also equal to 8. MC equals to 8, the second half. So here we define the center of the semicircle. This point is point O. We join points O and P together by a straight line. OP is of course the radius of the semicircle, that is 5. OP equals to 5 units in its length. OA is also the radius of the semicircle, that is 5. So what is the length of the missing 9797 OM? From the drawing it is very easy to see that OM in total equals to AM minus AO. Again, AM minus AO equals to OM. So I write it down. OM equals to AM minus AO. So OM in total equals to AM. AM is 8. Minus AO. AO is the radius of the semicircle, that is 5. So in total OM equals to 8 minus 5, that is 3. So OM equals to 3 units in its length. OM, that's 197 OM equals to 3 units in its length. So in the next step, I'll copy the small right triangle PMO in a new page and we'll implement the Pythagoras theorem on this small right triangle PMO. The hypotenuse PO equals to 5 units in its length. We just right now found out that OM equals to 3 units in its length. And the missing side is PM. Here by PT is information for Pythagoras theorem. So actually, this is the right small triangle PMO that I covered from the original drawing according to the Pythagoras theorem. In this right triangle PMO, PO squared, that is the square of the hypotenuse, equals to PM squared plus OM squared. So I write it down. PO squared, that is the square of the hypotenuse, equals to PM squared plus OM squared. The hypotenuse PO equals to 5 units in its length, therefore PO squared is 5 squared, that is 25. And it is equals to PM squared. PM is the missing side, so we leave it as it is. PM squared plus OM squared. OM is 3, therefore OM squared is 3 squared, that is 9. So in total we found out that 25 equals to PM squared plus 9. Here we subtract 9 from this equation. And finally we get that 25 minus 9 is 16, so PM squared equals to 16. So here we take a root out of this equation. And you get that PM equals to the square root of 16, that is 4. So PM equals to 4 units in its length. So actually this is the missing side PM, this is equals to 4 units in its length. So in the next step, we implement the Pythagoras theorem on the big right triangle PMA. So I copied the big right triangle PMA in a new page and we will implement on it the Pythagoras theorem. The hypotenuse PA equals to x, that is the 97 that we are looking for in this question. We just found out that side PM equals to 4. We only found out that AM equals to 8 units in its length. So actually, this is the big right triangle PAM, that I got it from the original drawing. In this right triangle PAM, PA squared, that is the square of the hypotenuse, equals to PM squared plus MA squared. So write it down. PA squared, that is the square of the hypotenuse, is equal to PM squared plus AM squared. The hypotenuse PA is X. Again, that is the line segment that we are looking for in this question. So PA squared is X squared. And it is equals to PM squared. PM is 4, therefore PM squared is 4 squared, that is 16, plus AM squared. AM is 8, therefore AM squared is 8 squared, that is 64. So in total, X squared equals to 16 plus 64, that is 80. So if we found out that X squared equals to 80, here we substitute 80 by 16 times 5. So X squared equals to 16 times 5. So here we take a root out of this equation, and we get that X equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only with 5. So in total we found out that X equals to 4 times square root of 5 units in this time. From terms of numbers, it is equals to 8.94 units. So in both methods, we found out that the length of this side AP is equals to X. It is equal to either 4 times square root of 5 units. In terms of numbers, AP is equals to X is equal to 8.94 units in its length. Okay, so we finish with the second question. In the next step, I will summarize the lecture. We start with the first question, of course. The first question, our task is to find out the area of this green shape. So in the drawing, we have a semicircle, BC equals to 10, that is to say the diameter of this semicircle is 10, therefore the radius is 5. So OA, the radius of OB is 5, the radius of OC is also 5, and the radius of OP is 5. In addition, you know that PC equals to 8 units in its length. This is angle ABC, that is right angle. Again, our task is to find out the area of this green shape. So first of all, we join points P and B together by a straight line. By joining points P and B, we create a peripheral angle BPC. Peripheral angle BPC subtend on BC, that is the diameter of the semicircle, and according to rule 5, any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in size. Therefore, this peripheral angle BPC is a right angle, according to rule 5. So in the next step, we implemented the Pythagoras theorem on this right angle BPC. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. The hypotenuse on this right angle BPC is BC. Therefore, the square of the hypotenuse is BC square, and BC square must be equal to BP square plus PC square. Okay, again, the right angle BPC, according to the Pythagoras theorem, BC square, that is the square of the hypotenuse, equals to BP square plus PC square. BC is 10, therefore BC square is 10 square, that is 100, plus BP square. BP is the missing side, so we leave this it is, plus PC squared. PC is 8, therefore PC squared is 8 squared, that is 64. So in total, we should find out that 100 equals to PB squared plus 64. Here we subtracted 64 from this equation, and finally found out that PB squared equals to 100 minus 64 is 36. So PB squared equals to 36. Here we took out of this equation and finally found out that the missing side BP or PB is equals to the square root of 36, that is 6. So actually, this is the missing side BP, that is equals to 6 units in its length. So it is given us the question that AC is a straight line. So if we focus on the left side of the straight line AC at point P, here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of the straight line AC at point P? We have this angle that is right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the right angle APB, we define this angle as alpha. So this angle equals to alpha, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in the triangle. The big angle ABC is 90 degrees, this angle ABP is equal to 90 degrees minus alpha, therefore this missing angle PBC must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, that is the size of the big angle ABC. So this angle must be equal to alpha. So in the right angle PBC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in the triangle. In the next step, we prove that the right triangle ABP is similar to this right triangle BPC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if we prove that all the fingers of the right triangle BPC are correspondingly equal to all the fingers of this right triangle APB, and therefore those two right triangles are similar to each other according to angle similarity rule. So if again we should find out that the right triangle BPC is similar, this is the sum of similar, to the right triangle APB according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB of the right triangle APB over side BC of the right triangle PBC equals to side AP of the right triangle APB over side PB of the right triangle PBC, and it is also equals to side PB of the right triangle APB over side PC of the right triangle BPC. AB is the missing side, so we leave it as it is, over BC. BC is the diameter of the semicircle, that is 10. BC is 10. And it is equals to AP. AP is the missing side, so we leave it as it is, over PB. We have already found out that PB equals to 6 units in its length. And it is also equals to PB, that is 6, over PC. PC is 8. So in total, we have found out that AB over 10 equals to AP over 6 equals to 6/8. So actually, those two expressions are equal to each other, therefore we get the equation 1 from those two expressions that are equal to each other. So according to equation 1, we get that AP over 6 AP over 6 equals to 6/8. So here we multiply this equation 1 by 6 and finally found out that AP equals to 6 times 6 is 36 over 8. AP equals to 36 over 8. Here we divided both the numerator and the denominator of this number by 4 and finally found out that 36 over 4 is 9 and over 8 over 4 is 2. So in total AP equals to 9 halves. So okay, this is side AP. This is side AP, this is equals to 9 halves. Those two expressions are also equal to each other. Therefore we get the equation 2 from those two expressions. According to equation 2, AB over 10 equals to 6 over 8. Repeat again, if we found out that AB over 8 equals to AB over 10 equals to 6/8. Here we multiply this equation 2 by 10 and finally found out that AB equals to 10 times 6 is 60 over 8. Here we divided both the numerator and the denominator of this number by 4 and finally found out that 60 over 4 is 15 over 8 over 4 is 2. So in total we found out that AB equals to 15 halves. So actually this is side AB, this equals to 15 halves. So in the next step we implemented the law of cosines on this triangle PBO. Only to the law of cosines, this is angle theta, cosine theta equals to 5 square plus 5 square minus 6 square over 2 times 5 times 5. And again, according to the law of cosines, cosine theta equals to 5 square plus 5 square on 6 square over 2 times 5 times 5. 5 square is 25, plus 5 square that is 25, that is 50, on 6 square that is 36, 50 minus 36 is 14, over 2 times 5 times 5 is 50. So in total we found out that cosine theta equals to 14 over 50. Again, cosine theta equals to 15 over 50. We have to find out the value of theta itself. In order to find out the value of theta itself, we will operate the opposite function of cosine, that is arc cosine, on the result, and this will give us the value of theta. Exactly like the two function, the root is the inverse function of the square. When we operate the root function on the number 9, we get the result 3. Now if we operate the inverse function of the root, that is the square, on the result, we get the only number 9. So we operate the inverse function of the root, that is the square, on the result 3, and 3 square is 9. So by operating the inverse function of the origin function, we got the origin number, because 9 is the origin number. Operated the inverse function of the root, that is the square function, and you got the origin number, that is 9. We did exactly the same thing here. Operated the inverse function of cosine, that is arc cosine on the result, that is 14 over 50. 14 over 50. In this way, we get the origin angle, that is theta. So the opposite function of cosine is arc cosine. We operated it on the result 14 over 50. In this way, we get the size of angle theta. And now we found out that arc cosine 50 over 14 over 50 equals to theta, and theta equals to 73.74 degrees in its size. So if we found out that angle theta, this is angle theta, that equals to 73.74 degrees in its size. Okay, so the next step we found out the area of this segment BP. From the drawings, it's very easy to see that the area of segment BP is equal to the area of sector BOP minus the area of triangle BOP. And again, if we found out that the area of segment BP is equal to the area of sector BOP minus the area of the associated triangle BOP. What is a sector? A sector is a portion of a circle that is enclosed by two radii and the arc between them. And again, the green shape AOB is a sector. It is part of a circle with two radii and the arc between the two radii, arc AB. This is the angle theta, that is the angle between the legs of the sector. The area of this sector AOB equals to pi r squared, that is the area of the circle in total, times angle theta, that is the angle between the legs of the sector, or 360 degrees. We use this new formula in order to find out the area of this sector POB. The area of this sector POB must be equal to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 73.74 degrees in its size, over 360 degrees. R is 5, so r squared is 5 squared, that is 25, so pi r squared is 25 pi, times 73.74 over 360 degrees, so in total the value of this expression is equal to 16.088 square units. So the area of the sector POB equals to 16.088 square units in its size, minus the area of this associated triangle POB. In order to find out the area of this associated triangle POB, we go from the vertex O perpendicular to the base PB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And we have the rule that the perpendicular to the base in an associated triangle bisect the base. The base PB is 6, therefore half of it is free. So MP is free, and MB is also free. So OM is the height of the base BP, and the area of any triangle equals to the base times the height over 2. The base PB times the height OM over 2. BP is 6, OM is 4. Why OM is 4? Because in any right triangle we have the three numbers 3, 4, 5. It is very typical associated triangle, 3, 4, 5. So OM is 4 divided by 2. 4 over 2 is 2, and 2 times 6 is 12. So in total we actually found out that the area of this associated triangle POB is 12 square units. And the area of sector POB, that is 16.088 minus the area of this associated triangle POB, that is 12, is equal to 4.088 square units. So actually found out that the area of this segment PB is equal to 4.088 square units. Our test is to find out the area of this ring shape. The area of this ring shape equals to the area of the right triangle APB minus the area of this segment BP. And again, the area of the ring shape is equal to the area of the right triangle APB minus the area of segment BP. This is the right triangle APB. What is the area of this triangle? The right triangle APB. It is equal to the base AP times the height PB over 2. AP is 4.5, PB is 6 divided by 2. 4.5 times 6 is 27 over 2. 27 over 2 is 13.5 square units. So the area of this right triangle APB is 13.5 square units. Minus the area of segment VP, we already found out that the area of segment VP is 4.088 square units. So 13.5 minus 4.088 is 9.412 square units. So in total, we found out that the area of this green shape, that is the area that we are looking for this question, is equal to 9.412 square units in its size. Okay, so we finish with the first question. In the next step, I presented to you the second question, and we solved the second question using two different methods. Our task in the second question is to find out the length of line segment AP is equals to x. We have to find out the value of x. So in the domain we have a semicircle. We know that AB, that is the diameter of the semicircle, is 10, therefore the radius is 5. BC is 6. Again, and we also know that AP equals to PC equals to x. Therefore APC is an isosceles triangle. Again, our task is to find out the length of AP that is equals to x. We have to find out the value of x. So point O is the center of the circle, therefore OA is the radius of the circle that is 5, OB is also the radius that is 5, OP is also the radius that is 5. So by doing those construction, we can add the isosceles triangle, triangle POB. Why triangle POB is an isosceles triangle? Because AO equals to OP equals to 5. And we have the rule that in front of equal sides in the triangle there are equal angles. In the isosceles triangle, triangle POA, in front of those two equal sides we have those two angles that must be equal to each other. So this angle, if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. Likewise, in the big isosceles triangle, triangle APC, why triangle APC is an isosceles triangle? Because AP equals to PC equals to x. So in the right isosceles triangle, triangle APC, in front of those two equal sides, we have those two angles that must be equal to each other. But this angle equals to alpha, therefore the other angle must be also equal to alpha. So in the isosceles triangle, triangle APC, this angle is alpha, this angle is alpha. Therefore, this perpendicular angle must be equal to 180 degrees minus alpha, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the smaller isosceles triangle, triangle AOP, this angle is alpha, this angle is alpha, therefore this perpendicular angle must be equal to 180 degrees minus alpha, 180 degrees minus alpha, according to the same rule. In the next step, we prove that the small isosceles triangle, triangle APO, is similar to the big isosceles triangle, triangle APC. So I combine those two isosceles triangles in a new page and we prove that they are similar to each other. So actually, those are the two isosceles triangles that are copied from the original drawing. This is the big isosceles triangle, triangle APC, and this is the small isosceles triangle, triangle APO. So what those two isosceles triangles are similar to each other? First of all, those two angles are both equal to 180 degrees minus alpha, 280 degrees minus alpha, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are also equal to alpha, therefore they are equal to each other. So I can prove that all the angles of the big isosceles triangle, triangle APC are correspondingly equal to all the angles of this small isosceles triangle, triangle APO. Therefore, those two isosceles triangles are similar to each other. This is the sign of similar, according to angle, similarity rule. And from the fact that those two isosceles triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AC of the big isosceles triangle, triangle APC, over side AP of the small isosceles triangle, triangle AOP, is equal to side PC of the big isosceles triangle, triangle APC, over side PO of the small isosceles triangle, triangle AOP. Okay, so AC over P equals to PC over PO. AC is 10 plus 6, that is 16. AC is 16. over AP. AP is x, that is the line segment that we are looking for in this question. And it is equals to PC. PC is also x over PO. PO is 5, that is the radius of the semicircle. So in total, we found out that 16 over x equals to x over 5. Here we cross multiplied this equation and finally found out that x squared equals to 16 times 5. Here we took out of this equation and finally found out that x equals to the square root of 16 times 5. The square root of 16 is 4. Inside the root we left only with 5. So in total, we actually found out that the length of this 97 AP is equals to x. This is equals to either 4 times square root of 5 units. In terms of numbers, the length of this 97 AP is equals to x is equal to 8.94 units. So we finished with the first method. In the next step, I presented to the second method. How to find out the length of this 97 AP is equals to x according to the second method. In the second method, we use the rule that says that the perpendicular to the base in an isosceles triangle bisect the base. Again, we use the rule that says that the perpendicular to the base in an isosceles triangle bisect the base. Triangle APC is an isosceles triangle because AP equals to PC. AC is the base, that is 16. From point P, we go perpendicular to the base AC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And according to the rule that I mentioned, the perpendicular PM to the base AC bisect the base AC. AC in total is 16, therefore each half must be equal to 8. The first half is AM, that is 8, and the second half is MC, that is also 8. So AM equals to 8 units in its length. AO is the radius of the semicircle, this is 5. So OM must be equal to AM minus AO. Again, OM equals to AM minus AO. OM equals to AM, that is 8, minus AO, that is 5. So in total, OM equals to 8 minus 5, that is 3. This one last element, OM equals to 3 units in its length. So in the next step, I copied the small right triangle POM in a new page and implemented the Pythagoras theorem on this small right triangle POM. Actually, this is the small right triangle POM. This is the copy from the original drawing. PO is the hypotenuse, that is 5. We just now found out that OM equals to 3 units in its length. The missing side is PM. So according to the Pythagoras theorem, this small right triangle POM, PO squared, that is the square of the hypotenuse, equals to PM squared plus MO squared. PO is 5, therefore PO squared is 5 squared, that is 25, and this is equals to PM squared. PM is the missing side, so we leave it as it is. Plus OM squared. OM is 3, therefore OM squared is 3 squared, that is 9. So in total we should find out that PM squared, 25 equals to PM squared plus 9. Here we subtracted 9 from this equation and we found out that PM squared equals to 25 minus 9, that is 16. So here we took a root out of this equation and finally found out that PM equals to the square root of 16, that is 4. So the missing side PM equals to 4. This is the missing side PM, that is equals to 4. In the next step, I copied the right big triangle APM in an equation. We implemented the Pythagoras theorem on this big right triangle APM. So this is the big right triangle APM that I copied from the original drawing. AP is the hypotenuse, this is equals to x, that is the line segment that we are looking for this question. PM is 4. AM is 8. So according to the Pythagoras theorem, in this right triangle APM, AP squared, that is the square of the hypotenuse, or PA squared, that is the square of the hypotenuse, equals to PM squared plus AM squared. PA squared equals to PM squared plus AM squared. PA is x, therefore PA squared is x squared, and it is equals to PM squared. PM is 4, therefore PM squared is 4 squared, that is 16, plus AM squared. AM is 8, therefore AM squared is 8 squared, that is 64. So in total we should find out that x squared equals to 16 plus 64, that is 80. X squared equals to 80. We subtracted 80 by 16 plus 5. Again, we subtracted 80 by 16 times 5. So in total we should find out that x squared equals to 16 times 5. Here we took a root out of this equation and finally found out that x equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only with 5. So in total we should find out that x equals to either that x equals to 4 times square root of 5 units. In terms of numbers, x equals to 8.94 units. So in both methods, we found out that the length of this line segment AP is equal to x. This is equal to either 4 times square root of 5 units in itself, or in terms of numbers, the length of line segment AP is equal to x is equal to 8.94 units. Okay, thank you very much.